So what is happening with regression, or is going to happen in regression, is that with regression we need to determine what is a dependent variable. Oh, finally it's here. So you can see the plot, right? So this is the plot. You can zoom it out like this. Anyway, so what with regression we need to decide. We need to decide what is dependent variable and what is independent variable. So maybe I'll let you decide which variables do you think should explain what variable. If you are in sales or marketing, or even if you are a property owner or an investor, I think you'll be interested in the price and you want to know whether it is your bedrooms, your beds, the number of guests, whether your property is a studio, all those features of the property that can determine the price. That's what you may be interested in. Because the price is easy to change than your beds or your bedrooms. Okay, so we can set a regression. We can determine a regression as a dependent variable as our price. So maybe let response as variable be price, and this be what? Regresses. So we can start. This is how the regression works. You look at the equation that we wrote in the slide. We had a dependent variable on the left and independent variables on the right. Okay, so it can be a simple linear regression or multiple. And the regression can have an intercept, or it may not have an intercept. Okay. And the function is the LM model. So basically what is happening is that we have a linear model which is saying that we have our y equal to our x, and then we feed the data to it. And our data is all underscore new, which we don't actually need, but because you already attached the data. So it's basically B0 plus B1x. So let's say x1. If you have more, it's going to be B2, x2 plus all the way, let's say BK, xk plus our error term. Oh, we don't have to write the error term anyway, so plus, let's say, ek. So this is what is happening here. What we are doing is that I got our data and we have everything set. So we run this regression and this is our coefficient. So what is happening is that this is how you interpret the coefficients, as you may know already. The intercept, which is basically in the absence of number of bedrooms, the price of the property is going to be 3,656, I believe, in USD. This is global data, so across all countries, this is the average price. Remember, this is a mean regression, so everything is in averages. But if you look at this, it means that for every increase in bedrooms, the price of the property is going to increase by 6,574. So there's only one variable, so we don't even have to bother with holding others constant. But the question is, are these significant or not? So we need to test the hypothesis of our estimate being equal to 0 or not. Okay. So this will give you more diagnostics output. So we have a standard error which is way less than our estimate. That is a good sign that our estimate is significant. We also have a t-value, which is in absolute terms greater than 2. That is also an indication that estimate is significant. And we have a p-value that is basically 0. And for R, they even provide indication of significant coefficients. So the 3 stars correspond to 0 p-value, 2 star will correspond to 0.1%, and 1 star will correspond to 1%. And you may have a dot, which will correspond to 5%. So the bedrooms is also a good indicator of price. Okay. Again, if you fit your model, you may want to know if the model, you want to know if your model is adequate in some sense. So what we want is to look at the goodness of it. How well does your independent variable explain the dependent variable? So in this particular model, how well, to what extent can bedrooms explain or determine the prices? And we have about about 12%, which is not enough. So that's our R squared. But there's a problem with the R squared. I will show you briefly. R squared has a problem of increasing every time you increase your independent variables. So there should be a mechanism to correct that. That mechanism is the adjusted R squared, because we want a model that has as few variables as possible. So adjusted R squared tends to institute the punishment for adding more independent variables, and it was likely to be less than R squared. So you see that's a little bit less than the adjusted R squared, than the R squared. Okay. Now, one of the conditions we said at least one of the independent variables should be related to the dependent variable, and that is the F test. So the idea, the hypothesis is that all the independent variables are simultaneously equal to 0, or the correlation between all the independent variables and the dependent variable is simultaneously 0. And the p-value for that is obviously 0. So that's an indication that there's some form of model that exists, because then at least one of the independent variables can explain the dependent variable. So at this point, our model is not bad. Now back to the issue with adjusted R squared. There's a mechanism called information criteria. So you have several models. You can use information criteria, which gives even firmer penalties for other independent variables. And that helps statistically to choose a better model instead of R squared. So with model 1, what I want us to test was, I think there was toilets. That was not, they did not have a significant relationship with price. So let's test that. I hope you noted. So if you do that, so let's see. Okay. Okay. So do you remember that it didn't have a significant correlation with the price, and that shows here, you see that the relationship here is insignificant. If we remove bedrooms from it and leave only toilets, what do we see? Again, that has not changed. The relationship does not exist for price and toilet, even though it is significant. Even though it is negative, it does not exist. Okay. So we have confirmed that as regression is correlation is a precursor to regression. Okay. For some reason, it's not always that your intercept is important in your regression model. So you may want to remove the intercept, and if you take if you subtract 1 from your intercept, from the regression model, the intercept will go away. So that can be our M3, and realize that with M3, there's no intercept, just the independent variables specified. Okay. There's also a quick way of using all your independent variables in the regression model at once. And if you look at this carefully, you realize if you put the dot sign, it will pick out all the other independent variables in the table into your regression. So that will be M3. So you see that it has used all the independent variables at a go. And now, for some reason, because of the interaction of all the independent variables, toilet is significant, but studio is insignificant. Let's take note of that because we are going to use it briefly. So we are at R3, right? There's a function called update, which is in the stats package, where you can update your regression model without having to write the model again. So if you take R3, which is here, you can update your R3 by adding a new independent variable or taking some of them out, or taking your intercept out, or making other interactions. So if you take this one, let's take studios out because studios is insignificant. Okay, so that will give us a new model M4. So if you write summary M4, that gives us a new model without the studios, which was insignificant. And you see that now everything is significant now. We can also update by removing the intercept. So M5, let's see how M5 looks like. So intercept is gone. Now studios is insignificant. See how the relationships change. And we can add another one, some interaction with what? Bed and bedrooms. So that's M6. Okay, so we can do that as well. It's an interaction. Okay. So before we continue, I want to show you what I was referring to, the weakness with adjusted R-squared or R-squared in general. So we use what we call the information criterion, and I think one common one is the AIC. So you can take AIC and put your model into M1. You have an AIC for M1. Can do that for all the models. So M2, so M2, M3, or we have M6, right? Up to M6. So 3, 4, 5, 6, 5, 6, 4. So this goes away. So there's a rule of thumb for the AIC. You choose the model that has the least AIC. That will be your best model. So if you run through, we choose the model of the least AIC. So we can go through it and pick the one with the least AIC as our model. Okay. Few things before we go on. So we maybe want to save your output. So let me save, say, M5. I can save the summary into S and capture it as a text. That will go into our working directory, and you can view it for use. Now, so you see the sum in the regression output that we saw. Okay. So the diagnosis that we did, like the F statistic was for the dependent variable goodness of fit. All the T statistics, the significance that we're checking were for the independent variables, but we haven't really looked at the residual, which is very important. So you can look at the residuals, a number of them. The mean it should be 0. It should be linear. Should have the variance should be constant. What else? Yes, some of those things. So we can extract the residual with the resid function. So whichever model that we choose, so let's say we choose model 3 or model 2, we can extract the residual. It will be a series. So for all the values, there will be a residual, and we can look at the mean of that, which is 21.8. That's a big problem. It's supposed to be 0, but that's for the M2. M2 is the one that will remove the intercept. But if you do it for M1, for example, for M1, you see that it is 0. So the specification of the model matters. So M1 is a little bit nicer. So let's use M1 to continue with our description. So we are checking it for the mean is satisfied. How about normality? Let's check and see. We can't be sure, but let's make it a histogram and see. That is not really something looking like a normally distributed residual. Let's look at QQ plot that we checked. Again, it doesn't look like normally distributed. Okay. But what is causing that? There may be some values. We have leverage, you have influential values, you have outliers. All of them can be impacting this relationship, and we can look at them via different plots. There are a lot of diagnostic plots that we can find for our model, a lot of them. So there are some particular values that are influential. If you look at these numbers on the far right of the KQR plot, they are the ones causing the non-normality of the residual, and that affects the model. The relationship between the scale and the location. So the scale is basically for the residuals. Realize that they are way apart. So the variance is not constant. You can see that. So it's heteroscedastic. You expect the fitted values and residuals to have some linear relationship or purely random. That's not happening. Okay. We can look at another plot, which is basically the same. So that is, I think, the size of my plotting space. Now that it is big, let's see if it will come. So exactly the same thing. Now you realize that this is from ggplot2. So it looks nicer, but it's the same plot. We can make this scatter plot. Suppose that it is the same as the M1, then the output will be the same. But M1 was just for bedrooms. So, but we can make it for other plots. That gives us the same thing, but not as nice as the ggplot. So you see, this one is from base R, so it's not that nice. Okay, let me skip this one. This is if you are trying to standardize it. Let's go to, this is already done. Test of outliers. Outliers will also not give you your what? Normality in your residual. So if you run this line, see the test of, these are all the values that are outliers. Look at them. You can always pick out the outliers. These are the outliers that are given, and they are corresponding p-values based on the Bonferroni test. There's a function called the global test of model assumptions. So that is in the GV LMA function, and that will test all a number of the assumptions for your model at once. So if you run it like this, you see that it has tested the linearity assumption here. So this is the model assessment of the linear model assumptions. So for tested skewness, link heteroscedasticity, which you need your homoscedasticity. So it's going to test all of them for you as many as they are available in the model. Okay. And for time series data, you can test the Devin Watson. The Watson is checking serial correlation in the residuals, and that the assumption is that there's no serial correlation in the residuals for any subsequent residual for a time series. You can also test for multicollinearity. Multicollinearity is trying to check if your variables are not independent variables are not too strongly correlated. If they are strongly correlated, chances are they are measuring the same thing, so you don't have to keep both all of them. So you have to remove some of them based on the correlation. They are supposed to correlate, but they shouldn't be too strong. That will be a problem for your model. Okay. Fewer than two items. So model one has only one item. So if you take for model, say 5, it will work. May not be sensible, but they are given. The VIFs, the rule of thumb is that maybe they should not be greater than 5. If they are greater than 5 in some context or in some literature is greater than 10, they need to suspect multicollinearity. So if you use the 5 rule, bedrooms may be taken out. But if you use the 10 rule, then you can leave all of them because they are okay. For 5, you may also talk about bathrooms. And I think that's the same test here. So test is non-constant variance with homoscedasticity. And realize that the variances are not constant, okay, of the residuals.